All right, so the things we're going to need for today's class, we're going to need the unit circle. We're also going to need the unit circle functions values chart. Okay, we're going to use these two things to solve some trig equations. And I'm going to bring up one note. Okay, and I believe the last time we left off, we talked about a linear, we talked about linear method. We talked about, and a linear method again, for a linear method, just as a quick review. All right, let's say we have 2x plus 4 is equal to 10. So notice that this is a linear equation, right? My variable is x, and x is raised to the first power. So any linear equation is an equation in which you have a variable that's raised no higher than the first power. In order to use this linear method, we basically isolate for the unknown variable. Okay. So in this instance, I'm basically going to solve it for x. So the first thing I'm going to do here is subtract 4 from both sides. Right, so I subtract 4 from the left-hand side. Right, 4 is canceled. I subtract 4 from the right-hand side. 10 minus 4 is 6. Next, I'll divide by 2. So I have x equal to 3. Right. I can also check, right, my solution. I can go back to my original equation. Okay, so you always go back to your original equation. And I'm going to substitute x for 3. And if x equal to 3 is a solution, it would make both sides equal. All right, so we know that once we substitute in x for 3, we have that both sides are equal. Now I'm going to compare this to a trig equation. All right, so remember that an equation is anything with an equal sign. So here is one that is, okay, similar to your problem number 1. And the directions, let me just bring that up real quick. They want us to find all solutions exactly on the interval you may see it written like this from 0 to 2 pi in some problems. So notice that for 0, all right, there's a bracket, which means we can include 0 as a solution. But notice for 2 pi, there is no bracket, which means we can't actually use 2 pi as a solution. Okay. Or you may see this interval written like this. 0 is less than or equal to theta is less than 2 pi. Okay, so both of these notations are one and the same. One just uses inequalities, and the other one is written like in an interval notation. All right, so here we're asked to solve 2 sine theta is equal to negative square root of 2. All right, so upon solving this, the first thing we need to know if it's either a linear equation or a quadratic equation. So keep in mind that for our trig equations, our unknown is this angle measured theta, right? And notice that my sine function is understood to be raised to the first power since I don't see any power. So this would in fact be a linear trigonometric equation. So in order to solve it, we're going to isolate for theta. Right, so the first thing I'm going to do here is I'm going to divide both sides by 2. So I have the sine of theta is equal to negative square root of 2 over 2. Right, so notice we've isolated for the sine of theta. right? So this is how we're going to interpret this. What angle in the interval from 0 to 2 pi has a sine, and remember that the sine is the y value of negative square root of 2 over 2. Right, so what angle in the interval from 0 to 2 pi has a sine or a y value of negative square root of 2 over 2? All right. So notice that our answers are angle measures. So I'm going to go back to now here you have a choice. You can actually use this unit circle function values, and notice it'll give you all 6 trig functions. You can also use the unit circle. However, the unit circle, it only gives you the cosine and the sine, right? So if you're finding like secants or cotangents or that sort of thing, the unit circle may not be helpful to you because you'd actually have to figure those things out. All right, but if we take a look at the unit circle function values chart, notice that all 6 trig functions for all of our angle measures are given right on this particular page. So I'm going to look at the sine, right? And I want to find all of the sine values that are negative square root of 2 over 2. All right, so as I scroll down, I see that the sine of 5 pi over 4 is negative square root of 2 over 2. So 5 pi over 4 is one of my values. And if I scroll further down, I see that 7 pi over 4 also has a sine value of negative square root of 2 over 2. Right, so those are my two solutions. Five pi over 4 and 7 pi over 4. Right. So now, like the algebraic equation that we just saw, we can actually check the solutions. Okay. So now this is optimal whether you want to check every solution or not. So I'll check like a few of these. All right, so I'm going to go back to my original equation. All right, so here's the check. So our original equation is 2 times the sine of theta is equal to negative square root of 2. And I want to substitute. Remember, you can only substitute one value at a time. So first we're going to check 5 pi over 4. So I'm going to substitute theta for 5 pi over 4. So we have 2 times the sine of theta, in which we're substituting for 5 pi over 4 is equal to negative square root of 2. I next want to evaluate the sine of 5 pi over 4. Right, so if we go back to our function values chart, the sine for 5 pi over 4 is negative square root of 2 over 2, right? So we're going to substitute that in for the sine of 5 pi over 4. So that's 2 times negative square root of 2 over 2. And I'm going to bring down the right-hand side, which is negative square root of 2. On the right-hand side, the 2's are going to cancel. So we have negative square root of 2 is equal to negative square root of 2. All right, so we in fact have both sides equal. So we know that our solution 5 pi over 4 is a correct solution. All right, you could also substitute in theta for 7 pi over 4. right? So just to quickly go through this, notice that the value, right? So if I were to change the 5 pi over 4 to 7 pi over 4, for the simple fact that 5 pi over 4 and 7 pi over 4 have the same y value, right, which is negative square root of 2 over 2, right? Notice that 7 pi over 4 is also a solution. Right, so you can check these. All right, and that is called what you're using a linear method. All right, I believe we talked about quadratic methods. Okay, we had mentioned the factor and cancel method, but I want to bring up another method, and this is the square root property. So here's the square root property. It says that if a squared is equal to c, then a is equal to plus or minus the square root of c. All right, so here is an example. X squared minus 4 is equal to 0. Now, you could also factor and cancel this one. I mean, we can use the factor zero factor property because you can, in fact, factor x squared minus 4. However, we could use the square root property, right? So the square root property says that we have to isolate for the squared term, right? So in this case, I'm going to isolate for x squared, so I'm going to add 4 to both sides. So we have x squared is equal to 4. So now that we've isolated for the squared term, we can apply the square root property. So it says that if a squared is equal to c, then a is equal to plus or minus the square root of c. So I'm basically going to take the square root of both sides. If I were to take the square root of the left-hand side, the square root and the square will cancel, right? So I'm left with x. On the right-hand side, I must sprout a plus or minus, right? Because that's a part of the formula. Square root of 2. Excuse me, yeah, square root of 4. Right, so now if I evaluate the square root of 4 is 2. So I actually have two solutions, plus or minus 2. That means x can equal to positive 2 or negative 2. All right, keep in mind that we can check. Right, so in order to check, I'm going to go back to the original equation, x squared minus 4 equal to 0. Okay, keep in mind we can only substitute one number at a time. All right, so first I'm going to substitute x for 0. All right, 2 squared is 4. 4 minus 4 is 0. So in fact, both sides are equal. I could also substitute in negative 2. So I'm going to substitute x for negative 2. All right, so when you square negative 2, right, negative 2 times negative 2 is a positive 4. All right, so in fact, negative 2 is a solution. So let's take a look at a trig example, right, using this quadratic method. So I believe this is similar to number 9, and it is secant squared x is equal to 1. All right. So we have secant squared x is equal to 1. So notice we have, it's in fact a quadratic equation, right? Because the largest power is a square. So we're going to use a quadratic method. All right. Now, the two quadratic methods we're going to use in this course are the factor and zero factor method and the square root property. So notice this is already in square root property form, right? We have our squared term isolated, right? And we have everything else on the other side. So if we were to apply the square root property, if I were to square the left-hand side, right, the square root and the square will cancel. So I have secant x on the left-hand side. For the right-hand side, however, we must sprout a plus or minus, and we have the square root of 1. So the square root of 1 is 1, so secant x is equal to plus or minus 1. So we have two solutions. Secant x is equal to positive 1 or negative 1. All right, so we're going to interpret this as, because remember that the solutions are angle measures. All right, so even though we solved this and we got, a positive 1 and a negative 1, the solution are angle measures. So we're going to interpret this as what angle in the interval from 0 to 2 pi has a secant value. And remember that the secant value is 1 divided by x of plus or minus 1. All right, so what angle has a secant value or a 1 over x value of 1? Now I would really use this 1 over x value if I had a unit circle and a unit circle only. But since we have the function values chart, we can kind of look up the secant directly. All right, so here's what I mean. I'm going to bring up this function values chart. I'm going to look in the secant column, and I want to look for all of the angles that have a secant value of either positive 1 or negative 1. Right, so I see that 0 degrees, right, it has a secant of positive 1, so that's one solution. And as I scroll down, I see that 180 degrees, right, it has a secant value of negative 1, right, so pi is one of my solutions. And notice that I also see that 2 pi has a secant value of 1. But keep in mind that we cannot include 2 pi as a solution, right? Because our interval, all right, is from 0 to 2 pi, but not including 2 pi. All right, so we have two solutions. So x is equal to 0 and pi. All right. So now here again, we can check. So here's the check. We go back to our original equation, right, which was secant squared x is equal to 1. We can only substitute one value at a time. So here we're going to evaluate at 0. So we have secant squared of 0 is equal to 1. All right, so how do we evaluate secant squared of 0? The first thing we're going to do is we're going to find the secant of 0. We're going to find that value, and then we're going to square it. Right? So if we look up secant of 0, right? So the secant of 0 is 1. Right? So we're going to substitute 1 for the secant of 0. 1 squared is 1, so we have both sides equal. All right, so we know that 0 is a solution. And just visually also notice that pi would be a solution, because if we were to take the same check, all right, if I were to substitute x for pi, right, we have the secant squared of pi is equal to 1. And if you were to evaluate the secant of pi, right, notice that the secant of pi is -1. Right, so -1 squared is +1. So in fact, we know that pi is a solution. All right, so that was the quadratic method by use of the square root property. Now we're going to take a look at another quadratic method, and it is the factor zero factor property. Okay, so this is quadratic method. I'm just going to call this number 2. And this is factor zero factor. Okay, but this is what you should always look to do first, actually. All right, so just a quick example using an algebraic equation, x squared minus 4 equal to 0. So notice before we use the square root property, right, because we isolated for the square root. However, you could factor and use the zero factor property, right? So my last term is negative. That means one of my numbers is positive, one of my numbers is negative. So in this case, I'm going to use 2 and 2, right? Because if you were to multiply x plus 2 times x minus 2, we would get x squared minus 4. And now we can use the zero factor property. It says that we can take every factor and set equal to 0. So notice once we do that, we now have linear equations. So we can isolate for the variable x. So if we take the first equation, x plus 2 equal to 0, we can solve it for x by subtracting 2 from both sides. So we have one solution is -2. And if we were to solve for x in the second solution, or in the second equation, we would have +2. All right, and the same can be done with trig equations. Okay. So here again, you can check that, which we've done in the previous example. All right, so this is similar to number 8. 2 sine squared t plus sine t is equal to 1. All right, so notice that this is a quadratic equation because our largest power is a square. Notice we also have a first degree sine term. So when I say first degree, whenever you hear me say that, that just means that the exponent on that variable is a 1. we could not use the square root property because notice in the square root property, the only variable is squared. So notice we have two variables. We have the second degree and the first degree. For this instance, we're going to use the factor and zero factor method. Okay. So one thing about this method is that you must have your equation set equal to zero. So in other words, that's called, in mathematical language, it's called putting your equation in standard form. All right, so we're going to force it to equal zero. So I'm going to subtract 1 from both sides. So we have 2 sine squared t plus sine t minus 1 is equal to 0. Next, we're going to factor. So I'm going to make 2 sets of parentheses, right? And this is still equal to 0. So in the first set of parentheses, I'm going to put 2 sine t. And in the second set of parentheses, I'm going to put sine t. So keep in mind, we're actually doing a reverse FOIL method, which means that if we were to multiply our first terms, right, we should get the first term in our polynomial, in our trinomial. So 2 sine t times another sine t is 2 sine squared t. Next, we're going to determine the sign. So if the last sign is negative, right, one of the numbers is positive and the other number is negative. Okay, so there may be some trial and check that's to go on here. So I'm going to put a negative in the front and a positive in the back. All right. So keep in mind for your last terms, whatever you put in for your last terms, you must be able to get the last term of your trinomial, right? So there's only one factor of 1. That's just a 1 and a 1, right? So like a negative 1 times a positive 1 is a negative 1. 2 sine squared t times sine squared t, that's my first term, sine squared t. The middle term comes from the outermost and the innermost. So if I were to take my outermost terms, right, 2 sine t times 1 is 2 sine t, and those are the outermost. If I were to take my innermost terms, negative 1 times the sine of t is negative sine t. Those are my innermost terms. And now I'm going to add these two things together. So negative sine t plus 2 sine t is positive sine t, which gives me the correct middle term. Right, so I know that my factorization is correct. So now that we have it correctly and completely factored, I'm going to use the zero factor property. I want to set each factor equal to 0. All right, so notice that I now have linear equations. So for the first equation, 2 sine t minus 1 equal to 0, I'm going to isolate for sine t. So the first thing I'm going to do is add 1 to both sides. And lastly, I'm going to divide by 2. Right, so the sine of t is equal to 1/2. I'm going to solve the second equation, sine t minus 1 equal to 0, in a similar fashion. I'm going to isolate for the sine of t, so I'm going to add 1 to both sides. Right, and I have sine t equal to 1. So now what we're going to do is we're going to use that function values chart, and we're going to find all of the angles that have a sine of 1/2, and then we'll find all the angles that have a sine of 1. All right, so if I bring back up the function values chart, okay, remember that sine is the third column, so I want to look for all angles that have a sine of 1/2. So it looks like pi over 6, and also 5 pi over 6. So that's pi over 6 and 5 pi over 6. We want to look for angles that have a sine of 1. All right, so looking down our chart, we see that 90 pi over 2, or 90 degrees, has a sine value of 1. Right, so our solutions are pi over 6, 5 pi over 6, and pi over 2. And I'll kind of leave it to, I'll check one of these. I will check one. All right, so here is the check. All right, I'm going to go back to that original equation, 2 sine squared t plus sine if t is equal to 1. All right, and I'm going to substitute t for pi over 6. Right, so remember that I'll just write it out first. So this is 2 sine square pi over 6 plus the sine of pi over 6 is equal to 1. Right, so I'm going to look back at the function values chart, and we're going to evaluate the sine of pi over 6. Right, so the sine of pi over 6 is 1/2. So this is 2 times 1/2 quantity squared, right? Because the sine of pi over 6 is 1/2, and then we're going to square that quantity, plus 1/2 is equal to 1. Right, so from the order operations, please excuse my dear Aunt Sally. The first thing I'm going to do here is evaluate the exponent. So that's 2 times 1/4 plus 1/2 is equal to 1. Right, remember I have to square the numerator and square the denominator. Okay, next I'm going to multiply 2 times 1/4. So the 2 and the 4 reduce down to 1/2. Okay, on the left hand side, 1/2 plus 1/2 is 1. So we know we have the correct solution. All right, so the same things can be done when you substitute t for 5 pi over 6, and the same result should follow when you substitute t for pi over 2. All right, so any questions about anything thus far? So you can factor the trig equations. All right, at this time, I am going to give you a problem to do. All right, and this is similar to number 10. This is 3.5, number 10. And you want to find all solutions in the interval from 0 to 2 pi. And we have sine cubed t is equal to the sine of t. All right, so I'm going to give you about 5 minutes or so to attempt the problem, and then we're going to return with the solution. All right, let's return with the solution. Okay, now as it stands, right, this would actually be a cubic equation because the largest power is a 3, right? When we deal with problems such as these, we want to somehow, some way reduce our equation down to a quadratic. And normally when you deal with these type of problems, we can put the equation in standard form, right? So standard form just means to set it equal to 0. So I'm actually going to subtract sine t from both sides. So I have sine cubed t minus sine t is equal to 0. And then I'm going to factor. I'm actually going to factor out sine t. Right? So on the inside of the parentheses, I'm left with sine squared t minus 1. Right? So keep in mind, I haven't changed up the equation because if I were to go back and reverse the process and multiply, sine squared t times, sine t times sine squared t is sine cubed t. And then sine t times -1 is a negative sine t. Right, so I kind of reduced it down to a quadratic. Now I can apply the 0 factor property. So I can take both of my factors, and one of my factors is sine t. I can set that equal to 0. I can take the other factor, sine squared t minus 1, set that equal to 0. And I can solve. So notice that the first equation is already solved, right? It's already isolated for sine t, so we have the sine t is equal to 0. For the second equation, I'm going to use the square root property. So I'm going to add 1 to both sides. And then if I apply the square root property, I'm going to take the square root of the left-hand side. So the square root and square cancel. I'm left with sine t. The right-hand side has to sprout the plus or minus, right? Plus or minus the square root of 1. So the sine of t is equal to plus or minus 1. All right, so I need to find the angles, right, in the interval from 0 to 2 pi that have a sine of 0 and a sine of plus or minus 1. All right, so let's find all of the angles that have a sine of 0 first. All right, so looking at all the angles that have a sine of 0, we see that 0 radians has a sine of 0, and we also see that pi has a sine of 0. All right, so our first couple of angles are 0 and pi. Now we'll look for the angles that have a sine of plus or minus 1. So we see that pi over 2 has a sine value of 1. And 3 pi over 2 has a sine value of -1. So we have t is equal to pi over 2 and 3 pi over 2. So our solutions are 0, pi over 2, and 3 pi over 2. All right, so here again, keep in mind that you could check these values. All right, now we're going to take a look at one last problem. And it may take a minute to explain this, but this is similar to your number 7, 3.5, number 7. Okay, so here again, find all solutions in the interval from 0 to 2 pi. And we have 2 cosine 2 theta is equal to the square root of 3. All right. So find all solutions in the interval from 0 to 2 pi, and we have 2 times the cosine of 2 theta is equal to the square root of 3. All right, so keep in mind that this is a linear equation, right? Because the cosine is raised to no higher than the first power, so we're going to isolate for the cosine of 2 theta. So I'm simply going to divide both sides by 2. All right, so the cosine of 2 theta is square root of 3 over 2. So now before we sort of saw something that looks like this, right? The cosine of theta, right? So we went around from 0 to 2 pi. But this says 2 theta. So I just want to show something for a second. So remember that for this notation, 0 is less than or equal to theta is less than 2 theta. Excuse me, 2 pi. Right. So if our angle is 2 theta, that means we must multiply by 2, right, for our interval. So what I mean by that is 0 times, because here we multiplied 2 times theta, right, to get 2 theta. So that means I have to multiply this by 2, and I got to multiply that by 2. So 2 times 0, that's still 0. But 2 times 2 pi is 4 pi. So we actually have to find the angles in the interval from 0 to 4 pi. So we want to go around that unit circle twice. All right. So this is how this is going to work. So here are our angle measures. So we want to find all of the angles that have a cosine of square root of 3 over 2. Right. So I'm going to bring up that unit circle function values chart. All right, so cosine, we're in the second column, so we want to find all of the angles that have a cosine of square root of 3 over 2. So we see that pi over 6 is 1, and (11) pi over 6 has a cosine value of square root of 3 over 2. So we have pi over 6 and 11 pi over 6. Right, but that only gives us the angles from 0 to 2 pi. So how do we find the other angles from 2 pi to 4 pi that has these same cosine values? Well, here's what we're going to do to find those. I'm simply going to take these two angle measures, right, pi over 6 and 11 pi over 6, and I'm going to add 360 degrees or 2 pi radians. Right, and they would give us the other angle measures from 2 pi to 4 pi, right, that would have the same cosine value, because we're actually in fact finding coterminal angles. So I'm going to write this down here. So this is angles in the interval from 2 pi to 4 pi. That have a cosine value of square root of 3 over 2. Right, so I'm going to simply take pi over 6, right? Because it has a cosine value of square root of 3 over 2. And I'm going to add 2 pi radians to it. Right? Because that would spin us around the unit circle and it would put us in the exact same spot. It would increase the radian measure by 2 pi, but the cosine value would remain the same. Right? So remember there was a formula that we were using and it says that A over B plus C over D, that's equal to A times D plus B times C over B times D. And I'm just going to apply that here. So pi times 1 is pi plus 6 times 2 pi is 12 pi. 6 times 1 is 6. So we have 13 pi over 6. All right, so I simply added 2 pi radians to pi over 6. Right, so I just added, if I'm thinking about degree measures, I added 360 degrees, which forces to be a coterminal angle, and it would still have a cosine value of square root of 3 over 2. I'm also going to take 11 pi over 6, and I'm going to add 2 pi to it as well. All right, and I'm using this formula up here, right? A over B plus C over D. So I'm going to multiply 11 pi times 1, that's 11 pi, plus 6 times 2 pi, that's 12 pi. 6 times 1 is 6. So we have 23 pi over 6. 23 pi over 6. All right. Okay, now here's the second half of what we want to do here. Okay, these are all of the angles for 2 pi. However, these are all of the angles for 2 theta. However, we don't actually want 2 theta, we want theta. The reason being is because when we go to check this, right, using our original equation, we must substitute in theta, not 2 theta. All right, so this may make some sense in just a second. So what I want to do from this point is I want to divide by 2. I'll just put that here. Okay, we want to take all of these angle measures, the pi over 6, 11 pi over 6, 13 pi over 6, 23 pi over 6, and we want to divide by 2. Divide all double angle values by 2. All right, right, so let's see how that works. So we have, right, 4 values: power 6, 11 power 6, 13 power 6, 23 power 6, and we're going to divide each one by 2. So first let's start with pi over 6. So we have pi over 6, and we want to divide that by 2, right? But in this instance, I'm going to make 2 a fraction, so I'm going to put 2 over 1. And then remember the other formula that we're using, it says that A over B all over C over D. That's equal to A times C divided by, A times D divided by B times C. All right, so you can multiply the very top and the very bottom, and the bottom on the top and the top of the bottom. All right, so here I can multiply pi times 1, which is pi. 6 times 2 is 12, so I have pi divided by 12. Next, we're going to take 11 pi over 6. We're going to divide that by 2 as well. All right, so I'm going to treat 2 as 2 over 1. I can multiply the very top and the very bottom. 11 pi times 1 is 11 pi. 6 times 2 is 12, so that's 11 pi over 12. Okay, so basically what I'm doing is just multiplying the denominator by 2. So my other 2 angles are 13 pi over 12 and 23 pi over 12. All right, so these are the actual solutions. All right, so I'm actually going to check just to make sure that these are the solutions. All right, so remember when we check, I'm going to check one right here. We go back to our original solution, our original equation, which is 2 cosine 2 theta is equal to the square root of 3. And I'm going to substitute theta for pi over 12. Right, so this is the reason why we have to divide by 2. Because I can only substitute in theta. So this is 2 times the cosine of 2 times theta, which is pi over 12, is equal to the square root of 3. Next, I'm going to simplify the innermost parentheses. 2 times pi over 12. The 2 and the 12 are going to reduce down to give us pi over 6. If we were to look back at the function values sheet and evaluate the cosine of pi over 6, notice that the cosine of pi over 6 is square root of 3 over 2. The 2's are going to cancel, and we have the square root of 3 is equal to the square root of 3. So we know that pi over 12 is a solution. So this is the reason why we must divide our angle, our double angles by 2. All right, so I'll leave it up to you to check the rest of these: 11 pi over 12, 13 pi over 12, 23 pi over 12. They should all check out to make both sides equal the same value. Okay, so just to review on this problem, right, it was a linear trigonometric equation. So we isolated for the cosine of 2 theta. We then found all of the angle measures from 0 to 2 pi that had a cosine or an x quadrant or an x coordinate of square root of 3 over 2. And we found 2 power 6 and 11 power 6. In order to find the remaining angles, right, because remember we're finding all of the angles in this interval from 0 to 4 pi. So in order to find the other angles, we had to add 2 pi radians, right? And we found the other angle measures, 13 power 6 and 23 power 6. And then the last thing we had to do was to divide by 2, right? You must divide by 2. We divided by 2, we found the 4 angle measures, and we also checked one. Okay, but the other should check in a similar fashion. All right, so at this time, I am going to stop the recording.